You know, usually when we talk about traditional cybersecurity, there's this expectation of like rigid, inflexible rules.
Right, it's very black and white.
Exactly. It's like building a medieval fortress. You construct a stone wall, you write a firewall rule, and the system just looks at an incoming packet of data and says, blocked. You don't match the signature.
Yeah, and that's comforting, right? Because we like things to follow the exact instructions we wrote, line by line.
We do. But then you step into the world of artificial intelligence and cybersecurity, and, well, that comforting rulebook is just completely thrown out the window.
It really is. I mean, we're looking at a defensive landscape that is entirely murky. You're dealing with systems making probabilistic decisions on their own now.
Which is terrifying if you're used to absolute certainty.
Oh, absolutely. Traditional software has verifiable execution paths that you can unit test, but AI agents, they generate continuous probability distributions. That creates infinite untestable paths.
And that is exactly why we're here today. Welcome to this deep dive. Our mission for this session is to take your stack of CompTIA SecAI plus study materials, along with the MITRE Atlas threat intelligence frameworks, and, the latest cybersecurity research.
And distill it into the ultimate audio study guide for you.
Exactly. We are targeting the core of securing AI systems. We're going to cover everything from how attackers poison datasets to how hidden Trojans hijack pre-trained models.
It's a lot of ground to cover.
It is. But to make sure you're truly ready for the exam, we are capping it all off with a massive rapid-fire scenario challenge at the end.
Sounds great. But before we can actually defend an AI system, we have to unpack why traditional cybersecurity rules just fail here.
Yeah, let's get into that. What's the fundamental shift?
Well, let's look at the research from Peter Sahan at the Center for AI Standards and Innovation. He noted that adversaries have an 88% attack success rate against open source models.
Wait, 88%? That's huge.
I know, right? And they do it using automated probabilistic evasion. Basically, adversaries iteratively probe the AI for, low probability outputs that evade its guardrails.
I like to visualize the difference like this. Rule-based AI and traditional security is like a strict bouncer at a club checking a VIP list.
If your name isn't perfectly matched on the ID, you're not getting in.
Exactly, you're blocked. But deep learning is more like a highly trained detective reading body language and sweating patterns to spot a fake ID. The detective is powerful, sure, but they can be manipulated psychologically.
That's a great analogy. And because they can be manipulated, defenders can't just set a rule and walk away.
Right.
Since the AI is making dynamic decisions, strict human-in-the-loop oversight is paramount.
Human in the loop, right? So you need an actual person double-checking things.
Always. You have to enforce the principle of least privilege, severely restricting what data the model can access and what external tools it can invoke.
Got it. So if the AI is a detective, attackers rarely use a frontal assault. They don't punch the detective, they corrupt their training.
Yeah, they mess with what the detective knows.
Let's talk about the difference between data poisoning and model poisoning. Data poisoning is injecting malicious or misleading data into the training data set itself.
Right, and it's often really subtle.
Yeah, let's say you're building an audio AI for voice authentication. A stealth attack is a subtle form of data poisoning where an adversary slowly edits the audio samples over, say, 6 months.
They might introduce microscopic amounts of static or slowly pitch shift the accepted voices.
So it's barely noticeable day to day.
Exactly. By gradually shifting the data, the cumulative effect creates a massive blind spot. The model slowly learns to accept a wider, less secure range of frequencies.
And eventually, it just allows the attacker's own synthesized voice to bypass the system completely undetected.
Which is terrifying, but contrast that with model poisoning.
Okay, so if data poisoning is manipulating the ingredients that go into the oven...
Model poisoning is manipulating the oven itself.
Oh, I like that.
Yeah, model poisoning is the direct manipulation of the model's parameters or neural weights. This often happens in collaborative or distributed training environments,
Where multiple unverified nodes are contributing mathematical updates to a central model.
Right. The attacker isn't messing with the raw audio files in this case. They're changing the math that dictates how the model processes those files.
Okay, let me play devil's advocate. If I'm an advanced attacker and I've poisoned the data files, couldn't I just rewrite the basic checksums on those files to hide my tracks?
You'd think so, But mature environments use MLOps machine learning operations pipelines that don't just look at file sizes or basic hashes.
What do they use instead?
You have to use public key infrastructure, or PKI, cryptographic signing.
Oh. Yeah.
Even if an attacker alters the audio file and generates a new hash, they cannot forge the cryptographic signature without the private key. It ensures non-repudiation and data integrity across the whole pipeline.
So we lock down the ingredients in the oven
Yeah.
using cryptography. But poisoning doesn't always happen in some secret lab before deployment, right?
No, not at all. Sometimes it happens right out in the open through user interaction.
Which brings us to model skewing and biases. Skewing exploits feedback loops. Think of a smart voice assistant that asks you if it understood your command correctly.
Exactly. An attacker can repeatedly insert misleading content. They might use a botnet to constantly tell the system that a malicious command is actually benign.
And over time, this shifts the classifier's learned boundary between good and bad. My first instinct as a defender would be to just rate limit the IP addresses giving that feedback. Like, if one IP submits 10,000 forms, just block it.
Well, IT-based limits fail completely against modern botnets.
Really? Why?
Because they rotate through thousands of compromised devices. The defense has to use token-based authentication tied to verified user accounts.
Combined with sensible data sampling, I assume.
Spot on. That ensures no single user cohort can overweight the training data, no matter how many IPs they use.
Makes sense. And if we don't catch that skewing, it induces bias. Models experience what's called concept drift. They learn historical biases.
Yeah, they do. If you imagine a giant three-dimensional mathematical map of words, what we call vector space concepts, are clustered based on historical text.
So a model might incorrectly cluster the word doctor closer to male pronouns just because of the statistical skew of the historical data it was trained on.
Exactly. And in an automated fraud detection system, unmitigated bias might systematically deny legitimate transactions for a specific demographic.
Which leads to massive compliance violations and financial loss.
Big time. It requires continuous fairness and hallucination auditing to catch it.
But let's be real here. Most organizations aren't training massive AI models from scratch. They are downloading pre-trained models to save computational costs.
Which is smart financially, but it opens up a huge supply chain nightmare known as transfer learning abuse.
Right. An adversary manipulates a pre-trained model on a public hub. You download it, fine-tune it on your private data, and unknowingly inherit the malicious behavior.
It's called the carryover effect.
It's like buying a house with a hidden trapdoor already built into the foundation.
That's a perfect way to put it. And that leads to backdoor and Trojan attacks. A threat actor can embed a highly specific trigger into the model.
For instance, the model behaves perfectly normally, 99% of the time, passing all your basic tests.
Yeah.
But if it hears a specific trigger word, like Apollo,
It suddenly drops its security guardrails or leaks its system prompts.
wow, how do they even do that without getting caught?
Often through a clean label backdoor, the attacker poisons the data without changing the labels, so the malicious data looks perfectly normal during visual inspection, but it still mathematically embeds that hidden trigger.
Sneaky. So how do we defend against that?
Organizations use tools like DVC data version control, which acts like a time machine for your datasets, allowing you to maintain strict AI dataset provenance.
Okay, so to navigate all of these unique threats, from untestable paths to clean label backdoors, security professionals need a map.
Yes, and that map is MITRE Atlas, the adversarial threat landscape for AI systems.
While the traditional ID/ARO ATT&CK framework focuses on standard IT infrastructure, ATA is tailored entirely to AI, right?
Exactly. It introduces tactics that just don't exist in traditional software, like ML attack staging or manipulating vector databases.
And the stakes here are not theoretical. The ATLA's framework documents a real-world case study where a foreign tax authority lost $77 million due to an adversarial attack on their facial recognition system.
77 million. Yeah, and ATLAS is constantly updating to tackle new generative AI and agentic vulnerabilities.
Which is why understanding the mechanics of these attacks is so critical for the exam and, the real world.
Definitely.
All right, listener, it is time to put you in the hot seat. We are going to run you through a rapid-fire scenario challenge simulating the CompTIA SecAI Plus exam experience.
Hope you're ready.
We've got 7 topics with 4 questions each. The 4th question in every group is a performance-based question, or PBQ, testing how you apply the knowledge.
We'll give you a brief second to think of your answer, and then we'll break it down.
Let's kick off with Group 1, the fundamentals of securing AI systems. Question 1 for you. What's the fundamental difference in execution between rule-based AI and deep learning? Think on that for a beat.
So if you remembered that rule-based AI relies on verifiable deterministic paths, you're on the right track.
And deep learning.
It relies on artificial neural networks that autonomously discover patterns, which results in probabilistic, non-deterministic decisions.
Awesome. Moving to question 2. Why do non-deterministic execution vulnerabilities make traditional unit testing ineffective for AI?
Got your answer. It's because AI agents generate continuous probability distributions.
Right, they create infinite untestable paths, totally unlike the binary pass-fail validation of traditional software. Question 3. What architectural control mitigates the risk of an AI taking autonomous destructive actions?
You should know this one. It's strict human-in-the-loop, or HITO, oversight.
Ensuring a human operator explicitly approves high-impact decisions. Love it. Question 4. Your first PBQ. You are deploying an anomaly detection system. Which framework should you use to map adversarial AI threats, and what access control principle must govern the model's API?
Okay, 2 parts here. You use MITRE Atlas to map the AI-specific threats, and you apply the principle of least privilege to restrict the model's access to data and tools.
Nailed it. Let's move to topic 2. Data poisoning. Question 1. What is the difference between targeted and non-targeted data poisoning?
Well, targeted poisoning manipulates the model to misclassify a specific scenario, like ignoring a particular malware signature.
And non-targeted.
That introduces random errors to degrade the model's overall accuracy, just creating chaos.
Chaos, right. Question 2. How does a stealth data poisoning attack actually operate under the radar?
Think about the audio example we used. An adversary slowly edits the dataset over time with really subtle changes to avoid detection.
Cumulatively introducing a bias or vulnerability. Okay, question 3. What is the purpose of a golden dataset in preventing this kind of poisoning?
A golden dataset is a highly protected, curated dataset of normal and malicious content.
You use it to validate a newly trained model before deployment, right?
Exactly, to ensure no significant regression or poisoning happened.
Question 4, your PBQ for this section. Analyze an MLO's pipeline. What specific mitigation prevents an attacker from subtly altering training data files without detection?
Don't get tricked into saying hashes. It's implementing cryptographic PKI signing.
Because basic checksums can be forged, but PKI ensures data integrity and non-repudiation. Moving on to topic 3. Model poisoning. Question 1. How does model poisoning differ physically from data poisoning?
Well, data poisoning manipulates the raw files. Model poisoning directly manipulates the neural network's mathematical parameters or weights.
Perfect. Question 2. What specific architecture inherently increases your risk of model poisoning?
That would be collaborative or distributed training environments.
Where multiple unverified nodes contribute to a central model, making it easy to inject malicious weights. Question 3. In an extraction attack, how do adversaries use a shadow model?
They repeatedly query your public API, record the inputs and outputs, and use that synthetic data to train their own replica.
Essentially stealing your IP.
Yeah.
All right, question 4, the PBQ. A deployed model suddenly behaves maliciously, but your logs prove that training data was completely untouched. Trace the supply chain vector. What artifact was compromised?
If the data is clean, it has to be the pre-trained model weights.
An attacker replaced the legitimate weights with a modified version right before the retraining cycle. We are halfway there, listener. Topic 4. Introducing biases. Question 1. How does historical data clustering impact vector space embeddings?
Remember the map analogy. Semantically similar concepts are plotted mathematically close together.
So if historical data contains societal biases, those concepts cluster together, leading to biased logic. Question 2. What is the business impact of unmitigated bias in an automated fraud detection system?
It's catastrophic. The system may systematically deny legitimate transactions for specific demographics,
Leading to compliance violations, reputational damage, and financial loss. Question 3. What specific audit detects if an AI is confidently fabricating facts?
That's hallucination auditing. It checks if the AI is presenting statistically probable but factually incorrect info.
Question 4, the PDQ. A healthcare AI is occasionally misclassifying patient urgency. To balance automation with safety, what monitoring control should you set to trigger a human review?
You need confidence level monitoring.
Right, you set a threshold, like 85%, and if the model's confidence drops below that, it routes the case to a human queue.
Exactly.
Let's tackle topic 5, transfer learning attacks. Question 1. Define ML07, transfer learning abuse.
It's the exploitation of pre-trained model weights. where an attacker introduces vulnerabilities.
And those persist even after you fine-tune the model for a completely new task. Question 2. Why are open-source pre-trained models highly vulnerable to this?
Because organizations download them to save money, but they have zero visibility into how they were originally trained.
Which risks inherited backdoors? Question 3. What is the carryover effect in fine-tuning?
That's the trapdoor analogy. Even if your fine-tuning dataset is completely benign, deeply embedded malicious behaviors from the original model carry over to your final system.
Question 4. Your PBQ. A team downloads a pre-trained language model, fine-tunes it on internal HR data, and deploys it. It immediately begins leaking sensitive data. Identify the attack and the missing pre-deployment control.
The attack is a transfer learning attack resulting in sensitive data disclosure.
And the missing control.
Rigorous model performance validation against a golden dataset prior to deployment.
Almost done. Topic 6. Model skewing. Question 1. What is the primary mechanical vector for a model skewing attack?
Exploiting user feedback loops, the attacker repeatedly inserts misleading data to shift the classifier's boundary.
Question 2. Define concept drift.
It's the natural degradation of a model's accuracy over time because the real-world environment changes, making the training data obsolete.
Question 3. How does sensible data sampling mitigate skewing?
It limits the statistical weight of any single user or cohort,
Ensuring a small group of attackers can't dominate the retraining data. Question 4. The PBQ. An attacker uses a botnet to continually mark their own phishing emails as safe in your feedback loop. How do you configure the API gateway to stop this volume attack?
IP blocking won't work. You must implement token-based authentication combined with strict rate limiting. Tracking authenticated API tokens neutralizes the botnet.
Finally, topic 7. Backdoor and Trojan attacks. Question 1. What is a clean label backdoor variant?
The attacker poisons the data without changing the labels. The malicious data looks perfectly normal visually.
But still mathematically embeds the trigger. Question 2. Why do hidden triggers so easily evade continuous testing?
Because the model behaves normally on 99% of inputs. The payload only activates when the highly specific trigger is presented.
Question 3. What is the role of AML.M0008? Validate AI model.
It requires aggressively testing the model against known adversarial examples before deployment to uncover those hidden Trojans.
Okay, question 4, our final PDQ. An AI chatbot operates perfectly until the word Apollo is typed, causing it to immediately output its hidden system prompts to the user. Identify the Trojan and map it to the correct MITRE ATLAS tactic for exfiltration.
The word Apollo is an inserted backdoor trigger. This maps directly to the MITRE ATLAS tactic AML.T0024, exfiltration via ML inference API.
And time. Take a breath. If you kept up with that, you are in phenomenal shape. I really want to congratulate you on making it through this grueling machine speed study session.
Seriously, well done.
Mastering these concepts isn't just about passing the SecAI Plus exam, it is about defending the next generation of our digital infrastructure.
Yeah, it requires shifting your entire mindset. You aren't just building a static wall anymore. You're managing a living, probabilistic system where the threats are constantly evolving.
I want to leave you with one final thought to mull over. As these AI systems become faster and more deeply integrated into our networks, we're beginning to rely on AI to automatically threat model, deploy patches, and respond to AI-generated attacks in real time.
Right.
So here is the question. Are we rapidly approaching a future where cybersecurity is entirely machine versus machine, leaving human analysts completely out of the loop? And if so, when the machine inevitably makes the wrong call, who takes the fall?